So I will get right to the problem that we're trying to solve with our industry partner. It's about crane scheduling, as you heard earlier, and we have a large, long warehouse with multiple storage positions. And in this warehouse, you can imagine blocks being stored, and the cranes move those blocks around. When you see here, the left crane moves a block to another stack, and there are actually two cranes inside of this warehouse. And they have to be scheduled in such a way that they do not influence themselves and do not block themselves. So when you have a look at this, the position of the left crane, it starts at this girder position, moves to the left, and then the right crane can pick up another block and move to the position where the left crane previously was and put the block there. And in such a scenario, imagine you have a warehouse which is 400 or 500 meters in length. You have to schedule them in such a way that the influences of both cranes that they have on each other, because they have to avoid themselves, is rather low. And in the same time, the number of moves that both cranes can complete in 1 hour, for example, has to be maximized. So there are different quality criterions you can use in this scheduling scenario, being it number of conducted moves, travel distance, percentage, crane utilization, percentage of evasions that they have to do, and so on and so forth. So this is the problem that we have. Try to schedule them optimally. There is quite some literature out there that you can read on such crane scheduling problems, and they often differ in the ways that the warehouse, for example, is layouted, or in the ways that the positions of the cranes are marked. There are one-dimensional problems, there are two-dimensional problems, and three-dimensional problems, and also different constraints. So, for example, in some scenarios, the cranes can actually travel as they like and do not interfere with each other. But in those articles and in that literature that we reviewed or had a look at, it is most often the case that they interfere with each other. Where did we get the literature from? We found two surveys by someone called Boysen. So he actually did the surveys, not we, but we had a look at his survey, and the references are listed here below. In one survey, they just had a look at single crane scheduling, so just assign tasks to a single crane, moves to a single crane, and try to find this sequence of moves so that the crane does not always has to go back and forth, but rather intelligently picks up different moves on the way. And in the second survey they're talking about cranes with interference, and this is also the kind of crane scheduling problems that we are having a look at here. Out of these, I think it was over 50 papers that they surveyed here. Only 5 of those papers actually deal with a dynamic set of jobs. So a job in crane scheduling is more or less a move. So pick up this block, put it there. And since we are working in adaptive environments, the crane scheduling itself is dynamic in our case. So this set of moves that the cranes have to conduct grows and shrinks. It grows when a new move becomes known, and it shrinks when one move is conducted, because then it's removed from the to-do list. And out of these 5 publications, none of these describe any form of dynamic adaptation to changing process conditions. So, for example, you have a warehouse and suddenly a crane breaks down. You have to reschedule and assign all remaining moves to the crane that is still working, right? Or another example, and this is what we had a look in our research here, the crane speeds change. You have a crane operator that can drive the crane really well and works fast, and then you maybe have an unexperienced crane operator who is not so well trained in moving the crane and picking up blocks, and it takes a bit more time for him to conduct those moves. And this is what we focus on here in our work. So our scientific contribution to this field is that we try to learn from historical data. So we have a simulation environment where two cranes can be moved around, and we can send the planned schedule and the move assignment to the cranes, and they will simulate those moves. And the simulation then gives us information how long it took for the crane to move this block there and this block there and so on. And from this historical data, we can learn how fast the cranes are going. I have to say that the simulation will change the crane speeds at specific intervals. So this is implemented in the simulation. The optimizer does not know this, that the crane speeds change, and this is why we have to learn this information and use it in our optimizer so that the schedules can be optimized better. We will see the effect of this learning procedure later on. Another challenge is that we now have the simulation process on the one hand, and our optimizer on the other hand, and those two have to be kept in sync. So when a new move is created, the optimizer must know that a new move exists, and somehow when the crane speed changes, the optimizer should learn that the crane speed has changed. So we have to keep the problem state in sync between the simulated real world and the optimized, the optimizer, the problem that is optimized. So here you have an example where this, if we would not synchronize the real world and the optimization, something bad happens. When you look here, these are two space-time diagrams. On the left side here, you see the simulated real world. On the right side here, you see the algorithm view of things. So on the y-axis, we have the time, and we see that the left crane number one is this is the x-axis, and also displays the horizontal view of the warehouse. So this crane one is standing here, and then after some time it starts moving to the left. So when you look at the top from the warehouse, it moves to the left, and then it stands here, picks a block up, the arrow goes up, and then it moves to the right, and it puts the block down here. So the move was actually going from this position over some time to this position. The same is happening on the right crane, on crane number two. It moves first to the left, picks a block up, moves to the right, puts it down, and then it just waits. As time passes, we get different world updates. For example, the crane starts moving here, we get a world update, and this is reflected in the simulation. So when we have in the optimizer, when we have a look at the optimizer side of things, the optimizer believes that the crane is moving to the left. It then picks a block up, and it then starts moving to the right. And then we get a synchronization message. So we know at this point in time here, we receive a crane message, and the position of the crane is different in the real world than what the optimizer has predicted it to be, because the optimizer has a certain speed model implemented. So it first moves to the left. It has a speed model for picking up blocks, and it has again the movement speed model. And the optimizer believes that the crane is at this position, whereas in the real world, it's a little bit behind. So the crane position gets reset when we synchronize. And this desynchronization that happens here, or where we have to resynchronize such big differences in crane positions. Imagine if the hall is 100, 200 meters long. This is quite some distance that we are off. This is bad. What would be better is if you look at the second crane here, it first moves to the left, then it picks a block up, and it starts moving to the right, and puts the block down here. It would be much better if we get a synchronization message here again, receiving crane message. Our algorithm thinks that the crane is moving to the right, and at this very moment where we receive the synchronization message, we see, our crane is exactly where it should be according to the real world. So this there is no desynchronization in this case, not much difference between the optimizer and the simulated real world. The way this works is, as I mentioned earlier, we have on the one hand the simulation, and once an event occurs within the simulation, once the world state changes inside of this simulation. So for example, if a new move is identified that needs to be done, or if a crane starts picking up a block or dropped off a block somewhere, so the storage layout changes, we update the world state. right? So this world state update is then sent to the optimizer. It's an open-ended genetic algorithm, OEGA. This world state is sent to the optimizer, and the optimizer then synchronizes its problem state with this latest world state. It then runs for some generations and outputs the new best found schedule for this updated world state, sends the optimized schedule back, and it is applied inside the simulation. So the cranes are now tasked with the movement sequence that was optimized here. Then they start working on this new schedule, and then in the meantime, no world update or updates occur, but the algorithm continues to run. It runs the next generation, finds no improvement to the current best solution. Again, and suddenly in some generations later, it finds a new best solution and it sends the optimized schedule back. And then again, the simulation will be, the sequence that is executed in the simulation will be overridden by the new optimized schedule. So this algorithm never stops except if I stop it manually. Once again, if an event happens somewhere, the world state changes. This update is reflected in the problem state in the algorithm, and we then have to find a new solution for this updated world state and have to send it back immediately. Okay, so we did 6 experiments. Basically, we had 2 simulation scenarios where in the one scenario, we used certain speed distributions. It was a triangular distribution to determine within the simulation the current crane speed. So for every move, we sampled from a triangular distribution, and so we knew, okay, this crane will now move with this speed. This is the simulation, the simulated real-world process. In the second scenario B, the speed distribution itself from the left crane changed. So we made this look like every 10 minutes, a new crane operator enters the crane, and maybe this crane operator in general is faster, or maybe this crane operator in general is slower than his predecessor. So the crane in scenario B, the left crane in scenario B had varying mean speeds, whereas the right crane always had the same speed, mean 4 and min max 3.5. And then on the optimizer side of things, we used different heuristics to determine the crane speeds. We had constant heuristics that said, okay, our left crane drives with 2, 4, or 6 meters per second throughout the whole simulation run. And we had an adaptive heuristic where we tried to learn from historic moves at what speed the crane is currently driving. And for this, we used a simple linear model where we just combined the horizontal. So we knew how long a move took in the simulation. This is the move time t. And then we knew how far the crane drove horizontally during that move. That this is x. And we knew how high he had to hoist the block in total. Pick up, move, pull it down, pick up again, and this is y. So we had the distances and the time it took, and with this linear model, obviously you can then determine the speeds by learning the coefficients. And we also made it so that we only consider the last 4 moves that have been done for each crane, or by all cranes, and also included the latest moves that were completed within the last 2.5 minutes, because we wanted to only have a look at what's the current speed of the cranes, and we just looked back on the horizon 2.5 minutes, so we don't get old data with old move times that are not valid in the current context anymore. Quickly to the results, and then we're finished. On the left side here, you see scenario A, a static scenario where the crane the move distribution, speed distribution of the left crane does not change. On the right side here, the right 4 is the dynamic distribution. And you can see here on average, the cranes were driving with 4 meters per second. So with the constant heuristic that predicted in our optimizer, the cranes move with 4 meters per second, we could reach 250 moves successfully on average. And with our adaptive heuristic, which tried to learn from this historical data, we also achieved approximately the same number of moves. And when we under or overestimate the crane speeds, we get a little bit less of successfully finished moves. And in the dynamic scenario, we can also see that the learning heuristic performs best compared to the constant approaches. Especially, there's much more distance here compared to the constant version 4 also, when you have a look here, because it's a dynamic distribution in this case. Scenario B had a dynamic distribution for the left crane, and therefore learning these speeds proved effective. Yeah, and then it's just an example one where you see here in blue the mean speed that the left crane had in a dynamic scenario for this given amount of time. On the x-axis you see the seconds. So throughout 1 hour of simulation, it was here at 4 meters per second, then it slightly increased. The operator was a little bit faster and was around 5 meters per second, and it dropped drastically below 2 meters per second. And the orange series here that you see is what our algorithm, our optimizer, our problem model had set throughout the simulation. And what it assumed using the adaptive heuristic was the speed of the left crane. Sometimes we drive a bit even outside of the minimum maximum bounds. But in general, we can see that we can reach the target speed that really was present in the optimizer after some time. And with that, yes, we can conclude that keeping those optimization models, the problem model, the optimizer in sync with the real-world processes or the simulated real-world processes is proves effective. So the adaptive heuristic performed best concerning the number of moves that could be conducted within 1 hour. And yeah, this learning and adjustment just takes some time after when the model is so good that the predicted speed is right again. Thank you for your attention.